Hey folks, so I wanted to come up with a little something maybe to help some folks out because I felt like I had to move kind of fast going through some of this stuff, so hopefully this will be of help. Some other folks, if you're able to follow along pretty well, especially if you're in first period or seventh period, then you don't necessarily have to go through this because a lot of what I'm going to be talking about I covered pretty well, especially as I got towards the end of the day. So what we're talking about here is we're talking about linked genes. And so when we do that, we're going to start with a test cross. So when we do that, we're going to take our F1 offspring. Right now, I'm going to go ahead and change this real quick. And so I'm going to say these are big B, that's B. And I'm going to do W's for wings. And so what I'm going to do is I'm going to make my test crosses. So the first one I'm going to do is I'm going to take my dihybrid F1 offspring, which basically means they're heterozygous for both traits. And I'm going to cross that with my homozygous recessive individual, right? And so what we're going to find, and I'll draw the Punnett squares to show you, if I'm going to do this, right, so here are my two Punnett squares. And I've got my genotypes here for the different offspring. And so when I fill these in, I'm going to look at this, and here's my Punnett square. And if you want to pause this and fill in the Punnett square for some practice by yourself, go ahead, by all means. These are supposed to be little w's. That's a big, that's a little. Here's too little. So anyway, here's our Punnett squares. And so when I'm looking at this, if I'm looking at the expected phenotypes, right? So when I have my expected phenotypes, I have gray bodies, normal wings. I've got gray bodies and vestigial wings. That just means teeny tiny. I've got a black body and normal wings, and I've got black bodies and vestigial. Now, when I'm trying to figure out my probabilities of each, you can fill in your Punnett square to do this, and that would help you count up all of that stuff. Or we can do the probability thing like we had talked about a few class periods ago. And so looking at this, I know that there's a 50% chance to get a gray body, and there's a 50% chance to get normal wings. Now, if I want gray and normal, I multiply those, and so that gives me 1/4. And as I go down through the list, gray and vestigial, so vestigial is also 50%. So 50% times 50% is 1/4. And so as I go down, I'll find that the probabilities of the expected phenotype is 1/4 out of 1/4, 1/4, 1/4. And so I basically have a 1-to-1 ratio. I should see equal numbers of all four genotypes. Okay? And that happens because the genes are assorting independently. Just like if I'm flipping a coin, the outcome of one toss will not affect the outcome of another toss, right? Now, what if I were to tell you that my outcome was actually this, where most of my offspring look like my parents? Now, if I rewrite this, it's going to be like this, B, little v, and this is B, this is little w, this is little w. And so basically what this ended up with is most of my offspring look like my parents. And so remember, my parents were either gray with normal wings or they were black with vestigial wings, right? We're not seeing that equal distribution of the four genotypes. And so the question then is, why is that the case? And so it turns out it's because if we look right here, what we're saying is the genes are on the same chromosomes. And when we say that, that means they're linked. And so if one is going to change, it's going to drag the other one with it. So if we change the assortment of the body allele, we're going to change the assortment of the wing allele. Hopefully that makes some sense. And so what we can do then is we can use this to figure out how linked these genes are. And so we come back to our cross, right? So now here's the cross that we did. We got our P generation right here. Those were our parents. We take our F1 dihybrid and we cross it with our homozygous recessive right here. What we would expect, like we saw, was equal, right? So 1 to 1 to 1 to 1. So if I've got 2,300 offspring, in this case, I would have expected to have seen equal numbers of all 4 of them. But if we look down here, what I'm seeing is I have more of the parent's offspring with only some of the other phenotypes. Now, those other phenotypes that don't look like the parents, those are the recombinant phenotypes. So this is no longer a 25% distribution. If we were to calculate this, this comes out to somewhere in the neighborhood of like 42%. Okay. And so we see more parental phenotypes. All right. So that's when we know that they're linked. So the first thing that we need to do is we need to compare what we're expecting with what we actually have. And if what we have doesn't match what we're expected, then we know that these genes are linked. Once we've established if they're linked, then what we need to do is we need to determine the recombination frequency, how closely linked they are. And so basically what we need to do is we need to add up the recombinant offspring. Okay, so if I add those together, it's 391, something like that. You can pause it and add it together real quick. I'm going to divide those by the total number of offspring, which is 2,300. I'm going to multiply by 100 to give me a percentage, and I'll get a recombination frequency of 17%. And so what this means is we would expect to see about 17% of our offspring between these two genes with a recombinant phenotypes. And that's due to crossing over. We haven't talked about this in a while, but that crossing over thing that we had mentioned a few class periods ago, that's what's happening here. That's where we're getting the recombinant offspring. And that doesn't happen necessarily in straight up independent assortment if the genes are on different chromosomes. Okay. So then what we can do then, once we calculate the recombination frequency between two traits, we can map those out and create something called a linkage map right here. And basically we can use the recombination frequency to determine the distance between genes on a linkage map. And we measure those in map units, also known as centimorgans. Now it's important to note that this is not a physical measurement. I can't measure how many centimorgans it is from my apartment to our classroom. Okay. It doesn't work that way. This is all going to be relative distances. Okay. And we can use these recombination frequencies to see where on the chromosome they are relative to the other genes. Right. Now, something that's important to note that if the recombination frequencies approach, if they're too far away from each other, okay, so basically, if we're looking at this, like here's a gene map of fruit flies, right? And basically, the farther apart two genes are, the greater the recombination frequency between two genes, the more likely crossing over is going to occur. And that's simply because there is more space in between the two genes that crossing over can occur, right? So if I'm going to look at this gene right here, I'm going to look at this gene right here, crossing over can occur anywhere in between the two, right here, right? It's harder for crossing over to occur right here in between these two genes because there's less space for that to happen, okay? Whereas here, if I look at this trait and this trait, crossing over can happen anywhere in between these two, right? And we can ignore all these other traits because we're just looking at this first one and this last one. Okay. And so now, in order to, how we create a gene map is we use the recombination frequency. So the first thing that we're going to do is we're going to start with the genes farthest away. Okay. So I'm going to look at this one, and the highest frequency is 45. And so B and C are my genes that are farthest apart. Okay. And then I'll just draw those out. And I'll do that on the next slide. And so I've got my, here's B and here's C. Okay. And I know that those are 45 units apart. Right. And so the next thing then I'm going to do is start filling in the other pieces that I know, and then determine the final distances of anything that's left, right? So here's my chromosome. There's B, there's C. I know those are 45 units across, like I just drew. I'm going to pick other ones that I know. Like, for example, I know B and D are 40 map units. So I'll put B or D somewhere like there-ish because I know this is 40 units. Okay. I'm also going to do A and C. That's a good one I can do. A and C is 30. So I'll put A like here-ish, right? Because I know this is 30. And then what I can do is I can go through and I can figure out the other ones, right? I know A to D, so this right here is 25. I don't have B to C, but I know that I've got 40 right here, and I've got 45. Sorry, other way around. So I know that the distance between D and C is 5 map units long. And then between A and B, because I don't have that one, right? I know A to C is 30, and I know B to C is 45. What's the difference, right? Well, I'll give you a hint. It's 15. So those are my map units. So to kind of clean this up a little bit, right? Here's my chromosome. It's B, A, D, with C at the end. And so those are my genes in the order that they are and sort of the relative positions that they're at and stuff like that. I mean, I guess if I wanted to be technical, I would make this a little bit closer like this. And so that's figuring out our gene map. You have one example in the practice set that you're doing this using a table, but it'll work basically the same way. It's just the layout of the table is different. If you still have questions, I'll be around. Send me an email or something like that. I'll try to get to class a little bit earlier, especially for 6th period. I'll try to be around kind of partway into 5th period right before class starts. So if we need to take a look at this, you feel like you need to, we can. Otherwise, study hard, get some rest, eat a good breakfast, and I will see y'all tomorrow for the test. Y'all have a good night.